Hi, my name is Mr. Evangelista, and welcome to this episode of Evangelista Science. We're going to continue our lecture on energetics and thermodynamics. So here we have a calorimetry experiment, and what this does is we can measure the amount of energy released from this combustion reaction. We can measure the amount of energy released from this combustion reaction by measuring the change in temperature of the water over time. Now, a couple of things that we want to make sure that happen in our system. One, that all the energy goes from the reaction to the water. None of it is lost. That's why we insulate it. None of it is lost in the environment. That all the energy is transferred to the water. So this copper casing right here should not absorb any of the energy and should ideally transfer all of the energy from the reaction to the water. And also that the reaction is running at 100% efficiency. Now, with combustion reactions, if you're measuring those, if you ever see any smoke, that is a sign of incomplete combustion, meaning there was not enough oxygen available in your system for the reaction to actually react 100% efficiently. So all the heat is transferred, and that all of the reaction is going at 100% efficiency, and that we don't have any limiting reactants because of that causes incomplete combustion. And calculations that we can do with this calorimetry experiment come from this equation. McPat, MCP delta T, is equal to the change in enthalpy, or Q. Now, this variable right here, CP, is the specific heat capacity. It's the heat needed to raise 1 gram of substance, 1 Kelvin, or 1 Celsius. These are the same. And so something that has a high heat capacity, like let's say water. Water has a heat capacity of about 4.184 joules per gram times Celsius. That's a lot of energy that you would need to put in to raise water 1 degree. And so 1 degree change for water actually represents a large amount of energy. So a substance with a smaller heat capacity, you just add a little bit of energy and the temperature would raise significantly. So let's take a look at the problem. We've got 5.35 grams of solid ammonium chloride, and this is added to water to form 25 grams of solution. The maximum decrease in temperature was 14 Kelvin. What is the enthalpy change in kilojoules per mole if the molar mass is 53.5 grams and the specific heat capacity of the solution is 4.18 joules per gram times Kelvin? Now, a couple of things. So we're going to be using this equation, MCP delta T. Delta H is going to be negative if our reaction is a combustion reaction or a neutralization reaction. So if we're adding an acid to a base together, a neutralization reaction, or if we're burning something. That is not what we're doing here. We are just adding salt to a water. And so that is going to immediately take out B. We know that this is going to be an endothermic reaction. Delta H is going to be positive because it is not a neutralization or a combustion reaction. Those are the reactions that IB wants you to know are exothermic. Okay? If it were a combustion or a neutralization, then we would know that delta H has to be negative. Okay? So we're going to take the mass. Now they give us 2 masses here. And we want to put, this is all going to be based on what is being heated, or what is the temperature changing of, and that's of this solution. And so we're going to use this one. So we've got 25 grams, and the specific heat of this solution was 4.184. So times that, and the change in temperature was 14. And that's all going to equal Q. Okay? And so when we do this, we get joules. Okay? But they want to know in kilojoules per mole. So we need to divide this by the number of moles. Now to get moles, I just take grams and I divide it by the molar mass. This is going to equal about 0.1. This doesn't have to be so big. Okay, that's going to be about 0.1. So we need to divide by the molar mass there, or I'm sorry, the number of moles. And one last thing that we have to do is that notice that our specific heat was given in joules, but they wanted the enthalpy change in kilojoules per mole. And so we are going to have to divide by 1,000 to go from joules to kilojoules. And the only one that kind of look like that is going to be C.